Okay, good afternoon. Shortly, we will hear an interesting lecture by Dr. Felipe and Dr. Baier on Photonic Integrated Circuit at Fraunhofer Heinrich Institute on applications, opportunities, and fabrication confirmation. This is part of webinar series organized by Photonic Israel on various aspects of photonics. Photonics Israel operates within the Engineer Association as a cluster of photonics entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in this area and to encourage cooperation both within Israel and with photonics entities in the world. We are open to your suggestions and would love to help foster new local and international collaborations. My name is Shlomo Glaser. I'm the manager of Photonic Israel. This webinar, organized by OpTechDB, the Berlin Brandenburg Association, and Photonic Israel, with the support of Dr. Ami Yacobi from Rafael. Dr. Philippe is currently working on a project manager for several national and European projects. And in his research is focused on hybrid photonics integrated circuit for broad range of application fields such as telecom, datacom, next generation wireless network, sensing, and life sciences. Dr. Baier is heading the indium phosphide Foundry group at HHI that commercializes a generic technology for photonic integrated in the INPI. Dr. Philippe and Dr. Baier, the stage is yours.
Okay, thank you very much for the introduction. I hope we have our audio sorted. I guess you can hear me?
Yes, we hear you.
Okay, perfect. So I will start sharing if the computer got so let me. Yes. All right. Yeah. So as was introduced, my name is Moritz Baier. I'm heading the indium phosphide photonic foundry group here at HHI in Berlin, Germany. So I will give an introduction to the thoughts behind and the capabilities of our foundry services in indium phosphide. So what's the idea? Well, most of you will be familiar with the multi-project wafer scheme that is popular basically since the beginning of the 80s in the electronics world, where basic building blocks such as transistors, resistors, or capacitors were abstracted away from the technology into so-called process design kits. And those in turn could be sent around to customers who then use those building blocks to design their own application-specific integrated circuits. Many of those customers could submit their designs to any given tape out at a foundry, and then the foundry, as seen here on the left, on one wafer run can fabricate designs for many different customers. And so that allows to dramatically reduce the prototyping cost for customers of the silicon electronics world to get their ideas to first provable demonstration. And the idea for us is that we want to mimic this sort of success story in photonics, and namely in indium phosphide photonics. So we do exactly the same thing, multi-project wafer runs on a commercial basis since 2016, so 4 years by now. To do this, we have an entire ecosystem where I'm happy to say Europe is really leading the rest of the world in terms of open access technologies, and Fraunhofer HHI is one of the foundries as part of this ecosystem. We have process design kits available in many different tools that allow our customers to not only design the actual physical layout of the chips, but also do simulations all the way from beam propagation or FDTD, so deep physical levels, up to a circuit and system level. And you can even do nowadays nice things like schematic driven layout. For instance, you can use a circuit simulator in PPI photonics, for instance, and once you're happy with your simulations in there, press a button and, for instance, connect to a tool from Mentor Graphics to export your GDS, your design file that you then can readily submit to us, to Foundry, and get your chips fabricated. And using this flow, by today, we fabricated photonic integrated circuits for over 100 different customers, 100 unique customers. Most of those customers have much more than one design fabricated, so you get a grasp for the numbers of innovation that have become possible due to the scheme. The classical road in photonics would be to develop dedicated technology for each product, and for each idea you would have to develop your own processing technology to make it become reality. And for most things, this is simply prohibitive and too expensive. And so using our low entry costs, many people can realize their ideas rather simply. And the applications you can see here on the slide range from classical telecom applications, which are our main field of expertise, to all sorts of different applications, all-optical computing and neuromorphic computing, many different sensing applications, polarization sensing, or up to even quantum applications, like a quantum entropy source shown here for QKD applications. So in the following couple of slides, I will do two things. I will first show what our technology can do in terms of building blocks. So I've been talking about in electronics, you have resistors, capacitors, and transistors. I will show a couple of examples of building blocks that we offer in our technology, which are summarized in the right-hand table here. And then afterwards, I will give some details about examples that I can actually talk about from our customers of what actual photonic integrated circuits they realized using those building blocks. So one building block that we are particularly proud of at HHI is the polarization converter or polarization rotator. Classically, it's always been very difficult to handle polarization adequately in a photonic integrated circuit because all building blocks normally have strong polarization dependence. And we identified that once you bring polarization conversion into your platform, you can basically leverage the polarization dependence to your advantage rather than perceiving it as a disadvantage or a limitation. And so this polarization converter, as part of our PDK, offers over 20 dB polarization extinction ratio in the C-band and has around 1 dB of excess loss on chip. Another highlight of our technology is a very fast photodetector that is integrated in the technology. It has up to 50 gigahertz of bandwidth, around 0.8 amps per watt of responsivity, and a pretty low dark currents below 10 nanoamps, typically around 2 nanoamps at the normal bias operating conditions. Of course, our technology being an indium phosphide technology, we have a direct bandgap semiconductor, so it's very easy for us to achieve optical gain and therefore lasers on chip. So on this slide, you see the performance of our DFB laser summarized. It's a complex coupled DFB laser. It delivers around 10 dBm of output power on chip. Its wavelength can be set anywhere in the C-band by design, and you can even thermally tune it by around 3 nanometers. And because of that, it's a really small footprint device, you can actually modulate it up to 20 gigahertz. And so in the upper right corner, you see a PAN4 eye diagram operating the device at 50 gigabit per second, so 25 gigawatt. For cleaner eye diagrams, we have an electro-absorption modulator that operates at wavelengths above 1560 nanometers. Here's an eye diagram at 56 gigabaud with 8 dB extinction ratio. Yeah, so that's the more advanced way of transmit type functionality. But new in 2020, we actually introduced another building block to this end into our technology, which is a Mach-Zehnder modulator, which has 2 volts VPi and uses a traveling wave design to scale beyond 56 gigabaud. So here we are talking about frequency responses of around 60 gigahertz. It uses a push-pull configuration, which gives this extremely low VPi and also achieves an intrinsic zero chirp operation. And unlike the electro-absorption modulator, Mach-Zehnder modulator operates across the entire C-band, not just at red wavelengths above 15, 16 nanometers. On the laser side, we have also more complicated laser designs than a simple DFB laser. So shown here are results of a widely tunable DBR laser. It's a 4-section DBR laser using the Vernier effect that does not infringe, in case somebody wants to ask any patent violations or anything like this. Has a tuning range of 50 nanometers, so well above the entire C-band, and a side mode suppression ratio above 40 dB for all those wavelengths. And just like the DFB laser, it emits around 10 dBm or 10 milliwatts of power into the output waveguide. Okay, so those are the highlights in terms of building blocks, and now to some examples of what customers have actually been doing using and what kind of photonic integrated circuits have been made using those. One rather elegant example for quantum entropy source is depicted here. The chip is actually a rather simple design. It consists of 2 lasers, 2 DFB lasers, emitting at different wavelengths, lambda 1 and lambda 2. They are combined using a 3 dB coupler, so this is simply an MMI, and a photodetector. And because the 2 lasers emit at different wavelengths, the photodetector will see a beat signal, which is basically given by the frequency difference of the 2 emitting lasers. And if you now pulse one of the 2 lasers, the phase of each pulse will become visible on the pulses of the beat signal that is visible on the photodetector. And now, because the optical phase at which a laser starts oscillating is completely random, and this randomness really goes down to quantum mechanics, you have a random signal that you can measure, namely the phase of a pulse on a photodetector, which really is random on a quantum level. Which is shown by this correlation function here. So you have a correlation below 1 in 1,000, no matter what pulse you correlate with another pulse. And so this can be used for QKD schemes where you need quantum random number generation. Another example leveraging the aforementioned polarization rotators is this dual polarization transmitter, where we use a DFB laser that emits only in the TE polarization, which, as I mentioned earlier, normally can be perceived as a limitation because everything is strongly polarization dependent. But here we use a 45-degree polarization rotator to effectively convert 50% of the TE polarization into TM. That's shown by those 2 purple arrows here. And now we have an electro-absorption modulator, which also only affects TE polarization. So the yellow signal, data signal that you apply to this modulator will be imprinted onto only 50% of the optical carrier, namely the TE polarization. And now the next polarization rotator, which rotates by 90 degrees, effectively swaps the TE with the TM component. And so the last EAM, the last electro-absorption modulator, can now modulate the remaining continuous wave fraction of your carrier. And so this orange data signal will now be imprinted on the remaining purple arrow. And so you have a dual polarization signal exiting your chip, which we show here with 112 gigabit per second operation gross data rate, without ever having to split or recombine optical signals, as is normally the case in dual polarization schemes. Another rather interesting application of our platform is given here. That's a design that was done by the University of Princeton, and they actually started a spin-off company from this kind of idea, which is now luminous computing. The idea here is you have photodetectors and a DFB laser integrated on chip, and in the upper picture here you see the photodetector's output. So the photocurrent that comes out of the photodetector is fed into the DFB laser, which is down here. Actually, at the beginning, when we received this design, I thought they made an error, but they reassured me that no, this is exactly what they want to do. I just would not really understand why. And well, the reason then later on became clear when they published this paper. So the idea behind this chip design is you launch, say, one pulse, optical pulse onto your photodetector. It emits an electrical pulse, which goes into the laser. Now, you bias the laser below threshold, and you bias it such that one of those electrical pulses coming onto the laser is not enough to kick it above threshold. And so you see here sub-threshold responses coming out of the laser. It does not really start lasering if you flick it with one of those pulses. But if you have 3 pulses in rapid succession, the integrating nature of the DFB laser makes it such that you get a spike, because it basically integrates over all those 3 pulses, and then it gets above threshold and starts lasering for a brief amount of time. And so this is a strongly nonlinear behavior which you can exploit to implement all-optical neurons, which is basically the gist of this paper here. So it was a rather nice application of the platform as well. Another example that I like to show to address questions about yield is this 100-channel fiber Bragg interrogator that is based on 11 AWGs and 100 photodetectors. So in total you have 100 channels, each spaced by 1 nanometer. So it's a 100 nanometer wide interrogator. And as you can see from this rather messy plot, if you count and look very closely, all the 100 photodetectors work. And if I were to make this plot even more messy, which I did not for clarity on the slide, and overlay the simulation of the designer, which in this case was Bright Photonics from the Netherlands, over the experimental results, they match exactly. So this cyclic behavior that you see, that every 10th channel has a little bit of a lower responsivity because there's no flat top characteristics, that's exactly what was actually simulated. So it also shows you the strength of having a solid and stable process design kit, because you can actually predict this sort of performance on such a complex circuit. And yeah, all the photodetectors on the chips that we measured worked. So there was no fails or anything like that. Yeah. One more example on the polarization diversity on chip is a design that we actually at HHI patented now. It's a polarimeter. So it uses a 5x5 Mach-Zehnder interferometer loaded with polarization rotators in each arm, which basically makes it such that the 5 outputs of this big Mach-Zehnder interferometer show an interference pattern that is strongly polarization dependent. And if you calibrate this sort of chip properly, you do some linear algebra, you can basically, from measuring the photocurrents of those 5 channels at your output, you can deduce what was the state of polarization at the input. And so that's what's shown by this Poincaré sphere up here. Blue circles on this Poincaré sphere are states of polarization that we launched into the chip. And the red dots are the states of polarization that this chip measures. So basically the answer of your system. And so ideally you want the red dots to be exactly dead center on the blue circles, and they pretty much are exactly. So we have an average error of below 1 degree across the C-band using this device. So it's a very accurate polarimeter. And the nice thing about this polarimeter is, because we monolithically integrate photodetectors with it, it actually has an intrinsic bandwidth of 45 gigahertz or even 50 gigahertz. So to best of our knowledge anyways, this is the fastest polarimeter ever demonstrated. Yeah. There's also some applications on the RF photonic side. So our partner VLC Photonics from Spain realized this chip in our platform that basically consists of a directly modulated laser, an optical delay line, and a photodetector. And by using a closed feedback loop on a printed circuit board where this chip is soldered on, you achieve a nicely controllable free spectral range and oscillation frequency, in this case of around 7 gigahertz, that you can tune by a couple of megahertz. And it has a really high Q factor because it's a photonic chip. Yeah, I'm going to skip over this one. That's a flip-flop, optical flip-flop based on SOAs. And one thing I do want to show is a fiber Bragg interrogator that was developed by the company FAST Technology in Ireland on our platform. The nice message here is you see their sort of system that they commercially sell look like this. So it's a system based on a lot of discrete fiber optic components that are assembled into a big box, and they are all connected by fibers. And now they scale the system down into a much smaller box based on a photonic integrated circuit. The size is not really the main message here. What really helps such an application tremendously is that you have everything monolithically on one single chip, so there's no mechanical or thermal drift between the components. And so what you see here in this plot is the delta of the answer of your system, so the delta wavelength that is measured by the system that's based on discrete components. That's the red signal over 24 hours, and measured by the photonic integrated circuit system. That's the blue signal. And so eliminating all those drifts helps your measurement accuracy tremendously. You gain orders of magnitude in terms of accuracy and stability. So photonic integration is what I'm trying to say with the slide. It's not all about size and costs. It's also like it adds another scale in terms of stability. Yeah, because you can keep signals so stable with respect to each other on one single chip, you can also do things like generate terahertz signals from one chip. So what we do here is we have two lasers similar to the quantum random number generator I showed earlier, two lasers that are detuned in frequency. And because our DFB lasers are tunable in frequency, you can basically tune the beat signal that you generate if you launch this sort of signal onto a terahertz antenna, say. So we use such a chip together with our terahertz systems that we develop here in-house as well in the terahertz group, to show that we can indeed transmit a terahertz signal that is tunable from 800 gigahertz all the way to 1.4 terahertz. And you can continuously sweep the CW terahertz frequency to make things visible, like the water vapor absorption lines that naturally occur if you go through a free space path like I think in this case it was around 30 centimeters of free space propagation. Yeah, and the last example I'm going to show here is a demonstration by Microsoft, where they try to address the problem of switching wavelengths of subscribers in the WDM system rapidly. So normally, because you have in the WDM system lasers emitting at different wavelengths, which are tunable. If you want to now tell a subscriber to emit at a different wavelength, you have to wait milliseconds or even longer until the subscriber has its wavelength stable and under control and does not see any switch-on characteristics anymore. So this introduces a lot of latency to those systems. So what they aimed for here is nanosecond switching speed, and how they achieve this is by basically splitting different subscribers into different arms on this photonic integrated circuit and using semiconductor optical amplifiers as gates. So if they want to switch from one wavelength to another, they basically just turn on one SOA and turn off another. And they use this wavelength division multiplexing element and arrayed waveguide creating on chip to associate those SOAs with different wavelength channels. And because the carrier lifetimes of an SOA are nanosecond scale, so very fast, you can switch your wavelengths much faster than what is state of the art. Yeah. So with that's basically it on what I want to show in terms of photonic integrated circuits. If that struck your interest, and I hope it did, the question might be, how do you get started? So this entire ecosystem that we are part of is headed and brokered by JPICS in the Netherlands. So the typical scheme to get access to this sort of technology is you contact JPICS, you get handed all the necessary paperwork, sign a user agreement. In turn, you get the process design kit and all the necessary documentation. You either yourself or by contract ask us or a design house to make the design for your idea, send the design to us as a foundry, and after 4 months of fabrication, get your chips for testing, and once successful, have a proven prototype in hand without any technology development whatsoever. We also have not just testing partners in this ecosystem, but also packaging partners, because we do understand that many possible application fields are not necessarily well equipped to handle bare chips. So putting a chip into a module and an entire system is also something we can handle. Yeah. With that, I thank you very much, and I'm open for any sort of questions.
Is there anybody who wants to ask a question? If not, we will move to the second lecture. Thank you very much.
Most welcome.
Yeah, so video is on, so you should be able to see me. Hello, everybody.
Yes, yeah, we see you.
And now you should be able to see my slides. Can you see them well?
Yes, we see.
Perfect. Yep, so now to a different story. So at HHI, we have a long expertise on indium phosphide, as Moritz has presented to you today. But also since already almost 20 years, we have been working in another direction for photonic integration, which is a so-called hybrid photonic integration. Hybrid in the sense that we combine on the chip level different materials. And I want to introduce you today to this technology that we have at HHI, which we call PolyBoard. And also we want to show you some different application scenarios, which are currently being investigated in the framework of different European projects. So all this work that I'm going to show is carried out by the Hybrid Photonic Integrated Circuits group at HHI. Some of it in close collaboration with Moritz's group. So just to give a few words about our technology, which we call PolyBoard, here is just an idea of what we do. So we have the so-called hybrid photonic integration, meaning that we combine on a chip level different materials depending on the application that we are targeting, right? So we try to follow the best material for the function approach. So our technology is based on polymer waveguides, which serve as some sort of a motherboard. These waveguides are passive, which means that if we need to use active components, we need to go to Moritz and ask him, okay, can you do lasers for us, photodiodes for us? And these are the indium phosphide components that are being also developed at HHI, and we can combine it with the polymer waveguides for these active or optoelectronic functionalities. We are not only restricted with indium phosphide for the C and O bands, so the polymer materials are also transparent in shorter wavelengths, meaning that we can also couple active components based on gallium arsenide, targeting wavelengths of around 700 nanometers. And we can even go to shorter wavelength to the visible, and I will show you that later on. So we have also the possibility of combining our waveguides with other materials, such as, for example, lithium niobate, graphene, and even silicon nitride. So this is the idea: multiple materials all put together by means of a polymer waveguiding function. So this hybrid technology, which I already introduced, is called the PolyBoard technology. Here you can see some of the key features that we can implement on this polymer waveguide. So you can see here on the right hand side several pictures. So the top left are what we call U grooves, which are U-shaped structures on the polymer materials, so that we can have a passive fiber to chip attachment, and also we can use them to build up free space sections on our polymer chips. So to have some sort of a micro-optical bench in our platform. Additionally, we can etch some slots on the polymer waveguides, as seen here on the top right-hand side, on which we can insert thin film elements, which might be designed for different functionalities, for example, for wavelength filtering or for polarization handling, which means that in a very small footprint, these filters are between 15 and 25 micrometers thick. We can implement a functionality which is non-temperature dependent due to the electrical materials on which these thin film elements are fabricated. Another very interesting feature is what we call flexible interconnect. So the components that you see here on the top side, so the U grooves that I showed in these thin film elements, they are fabricated on top of a silicon substrate. And what we can do is to peel off the polymer to fabricate these flexible interconnection methods. They can be either optical or also high frequency, since polymer materials show a low dielectric constant, which is good for the high frequency capabilities of, for example, coplanar waveguides. And as a last very interesting aspect of the polymer integration are the so-called 3D photonic integration. So here on this picture, you can see a cross section of a polymer waveguide chip, on which each one of these small squares is a waveguide, and we can stack them up to achieve 3D photonic integration, which is interesting. For example, you want to attach to the chip multi-core fibers, or also if you want to overcome unending crosses in very complex waveguiding networks. So you can route different waveguides to different layers and then be able to route without increasing the number of interconnects. So this is a short perspective of these polymer waveguides, of what these polymer waveguides can do. And this schematic shows how these waveguides can be fabricated. So it's a fairly simple process. So that's one of the potentials of this technology, which is simple and therefore can eventually be low cost. So we start with silicon substrate, which is the darkest block here on this left-hand side picture, and we can coat on it with the bottom cladding, which has a specific refractive index. Then on top of it, we can spin coat the core material, which will basically structure our waveguide, which has a slightly higher refractive index as a buffer layer. And then by means of reactive ion etching, we can then etch down the areas where we want to have waveguides, the areas where we want to structure. And there we have already the channel waveguide. And then we can just coat it with a second polymer to protect it. And that's it. That's so simple is the fabrication process with these waveguides. They are multi-mode and single mode, so we can do both. Mostly we work on single mode. And another interesting aspect is that the refractive index of the polymer is very close to that of single mode fibers, so that of glass, meaning that if we want to couple a fiber, we don't need to polish, and we also don't need to coat. Basically, we can have a fairly simple fiber to chip attachment, fiber to chip coupling to our chips. So this is an example of one hybrid photonic integrated circuit. So this is an optoelectronic transceiver. So here you can see the fiber, which is attaching one of these U grooves. We have here in the center of the chip a filter, which reflects the light of a hybrid laser that comes that is implemented on this right-hand side. So the light generated comes to this filter, and then is sent up to the fiber link. And the data that is received will come at another wavelength and will go through and be detected by those photodiodes that are coupled to the polymer waveguides by means of 45-degree mirrors, as you can see them here. So this metallized structure here is a 45-degree mirror that allows us to couple the light out vertically from the waveguiding structure and be detected by backside illuminated photodiode. So you see a chip here comprised with different elements, and that's something that, of course, monolithic chips, they don't need to do. So we need to combine those elements somehow. So the question that you might be asking yourself is, okay, how do you do that? How do you couple those elements together? Is there a way to have this kind of photonic integration developed so that it can be able to cover large volumes of production? So I anticipate that the answer is yes, and we're working already on that. And one of the key aspects when we talk to large volumes, and also when we talk about packaging, are these so-called U-grooves that I introduced before, right? So these U-shaped structures on the polymer material, which allow us to insert the fiber. You can see here, this will be a fiber. This is a cross section of this U-groove. So the fiber can be placed in, and this structure is fabricated by means of etching in a very accurate way, so that the core of the fiber fits the core of the waveguide. So it means that this is kind of a plug and play structure. So you plug it in, you don't need to line, and then you have a coupling. And to understand how advantageous is to have such a method to couple the fibers, you can see here on the right hand side the comparison of the packaging costs in integrated photonics versus the packaging costs in silicon photonics. So the green part is the cost of packaging, of assembly. And a big part of this is basically the fiber to chip coupling. Not only, but a big part of it. So if we are able to achieve a low effort fiber to chip coupling, as we can provide with this polymer integration platform, we will be able to reduce this green area, and therefore we'll be able to make photonic components more affordable for all the different functionalities for which photonic integration is useful. That's one part. The second part is, okay, we also want to combine all these elements. So I showed this PIC with the fibers, the thin film filters, the lasers. So these different components can be coupled together by means of photonic assembly machines. And we have here at HHI a photonic assembly machine from the company Ficontech that allows us to carry out all these different functions that you see here. So bonding, active coupling, flip chipping, the assembly of micro-optical elements. I will show later on some videos that show this, but this is basically to state that we work very hard on automatizing all the processes that are involved in the hybrid integration of photonic integrated circuits. An example of a hybrid PIC, a very, very straightforward example, is a thin film based multiplexer demultiplexer, right? So I mentioned before, you can implement on these thin film elements filtering functions, so that, for example, if you want to transmit together to different wavelengths on a channel, that this element will allow you to split them and to be able to detect them separately. And this is the level of compactness that one can achieve with this hybrid integration method. And this is a very simple element, but the losses are very low. What you can achieve with this high function, so 1 dB losses, and the crosstalk between channels, meaning the crosstalk between wavelengths, can be reduced to lower than 30 dBs. Another key element in our technology platform is the so-called hybrid DBR tunable laser. So basically, the structure, as you can see here, comprises an indium phosphide active section that is end-fire coupled to a polymer chip. So this section here is a polymer chip on which we can implement thermoptically tunable phase shifters and Bragg gratings. Thermoptically, meaning that we can, by means of these microheaters, change the temperature locally of the waveguide, so heat it. And by means of the change in the temperature, the refractive index of the waveguide changes. And with that, we can achieve tuning of the lasing wavelengths, as it can be seen here, over a range of more than 20 nanometers. One key aspect of polymers is, firstly, they have a high thermoptical coefficient, meaning that for a certain change in the temperature, one can achieve a fairly large change in the wavelength of the laser. And also, the polymer material typically shows a very low thermal conductivity, meaning that if we generate heat on it, the heat will remain close to the waveguide and therefore will not be dissipated, which allows us to have a very efficient tuning mechanism on the polymer technology. And you can see here that on the right-hand side that for this 20 nanometer tuning, we need a power of more or less 40 milliwatts. So this is a very interesting element that we've been developing in the last 6 to 7 years. And it shows exactly the combination of the two best materials for each function, right? Polymers for the thermoptical tuning, and for the active part, we need something that is not polymers. We use indium phosphide elements developed by our colleagues the different groups that developed in the indium phosphide components. So the tunable laser concept can be extended also to other wavelengths. So I mentioned before that polymers are transparent in a very broad range of wavelengths. So the typical C and O band wavelengths for telecommunications, but also for spectroscopy application, it's interesting to go to shorter wavelengths. So 785 and 1064 nanometers, for example. And this is a tunable laser based on the same principle that shows that just by changing the indium phosphide, the active section from indium phosphide to gallium arsenide, and of course by redesigning the Bragg ratings to be able to design at that wavelength, one can achieve also a tunable laser operating at these wavelengths. And also I mentioned that polymers are also transparent down to the visible, meaning that with polymers we can unlock a broad range of wavelengths, meaning that we can achieve or we can develop components for a broad range of applications, such as, for example, life sciences and quantum technologies, where these short wavelengths are of crucial importance. Another aspect that is fairly important in our technology is the so-called micro-optical bench. So being able to implement on our polymer platform free space sections. And how we do that, you can see here in this cross section. So this is basically a side view of the chip. So this will be the silicon substrate. This reddish area is the polymer, and we can etch down the polymer there and insert on it graded index lengths, which function as a collimating component that would allow us to generate these free space sections on the chip. What for? So one could use these sections for implementing etalons, meaning wavelength filters that one could use to implement for example, a wavelength meter, as depicted here. But also one can use this free space section achieved on the chip to put in there any other material that one wants. And a very good example is to be able to introduce garnet materials to achieve non-reciprocal polarization rotation in order to implement optical isolators and circulators, as shown as depicted here in the lower right-hand side. So right now there's no stable or there's no optimal implementation of isolators and circulators on integrated optics. It's very common to have isolators and circulators in photonic packages, but by means of free space optics. What we can do here is we can put them on the chip so that we can simplify the whole assembly process. So this is a very powerful tool, this micro-optical bench, and you can see here an example of an optical isolator on the chip. So you can see here, this is the top view of the polymer chip with a green lens. So first we have a waveguide, a green lens, then we have these free space sections on which we can insert this garnet material, and then a second green lens, and then a waveguide, right? And so simply we can implement on a chip comprising other functionalities an optical isolator. And some of the key performance indicators of optical isolators are shown here in this graph. So basically we achieved on-chip losses of under 1 dB at 1550 nanometers, and peak isolation of 28 dBs in the C-band, with complete isolation of more than 20 dBs along all the wavelengths of the C-band. So this shows that with this fairly simple concept, we can implement crucial components in photonic integration, such as optical isolators and circulators. So all that, as mentioned, opens a broad range of possibilities. So I talked about the tunable lasers that one can implement. I've talked also about this micro-optical bench with which one can implement optical isolators and wavelength monitors. And basically one can combine all these elements in such a way, like in a Lego box system. So you can see here some examples of what we could do. So a chip with a tunable laser, an optical isolator on it, and also with a wavelength monitor based on etalons, right? So you could avoid any reflections on the laser and also be able to read out the wavelength at which this laser is lasing. And also one could combine tunable lasers with non-linear optical elements, which can allow you, for example, for second-order harmonic generation, which are effects that are currently being investigating for quantum technologies. So this opens a very broad window of possibilities for our devices. A final key characteristic of our technology are the so-called FlexLines I introduced in the beginning. So the chips that I showed until now, they are always on a silicon substrate. And what we can do, we can peel off the polymer from the substrate, and you can see on this top right-hand side slide, and then we have a flexible structure, right? And we can use these type of elements for optical waveguides, as you can see here on the bottom right-hand side, to achieve a flexible interconnection between PICS, for example. And we could also implement coplanar waveguides, high-frequency coplanar waveguides for interconnections between, for example, photonic components with optoelectronic elements, and the drivers and TIS, for example. And here on the left-hand side, you can see an example of the frequency response of one of such a coplanar waveguides, where you can see that the bandwidth is larger than 100 gigahertz. So this shows that it has a high potential as a high frequency interconnection method between electronics and photonics. So here I want to show a couple of videos with regards to the hybrid integration. So the technology, as you've seen, that it needs to have different parts. What you can see here on the right-hand side is the assembly of an isolator. So now the green lenses have been inserted on this polymer chip, which is on this chuck. And now one applies some glue here, on which we will fix the lenses. And also we will fix afterwards this garnet material for the non-reciprocal polarization rotation. So with image recognition, what can place this garnet element, this Faraday rotator, on this free space block on our chip. As you can see here, now it's been plugged in, inserted. And with that, I will also want to show that it's possible also to couple this indium phosphide element. And as an example, I will show you how to assemble a tunable laser using this photonic assembly machine from the company Photonic. So this is a polymer chip, which comprises already the U-groove, on which now the glue is going to be deposited, as you can see here. Now in another arm, we will pick up the fiber. This is a single mode fiber. It's picked up here, and using image recognition, the U-groove is identified, and then the fiber is inserted. And the final part is to couple the indium phosphide active section, right? So a drop of glue is positioned. Now this is the indium phosphide section, which is being actively aligned with the fiber that is inserted in the U-groove. And after the alignment is done, we can shine everything with UV, and then the assembly is finished. So this shows the automatization efforts that we currently carried out in order to be able to assemble such a components for medium and large volumes of manufacturing. So I'm coming now to the application part. We are working currently in 6 European projects. And they are covering a broad spectrum of applications. So data centers, metrology, 5G, and also quantum communications. So here you see the 6 projects. I will not go into them because I will be explaining one for one what we are doing and how is our polymer technology helping in those. So I will start with a European project called Terrific. Let me highlight here that we have an Israeli partner, so Mellanox Technologies. I think since this year they are part of NVIDIA. So we are developing then in this project a terabit per second transceiver. So the bluish part here is a polymer-based array waveguide grating, which acts as a wavelength multiplexer and demultiplexer. On the left side of this polyboard, you can see indium phosphide-based EML arrays coupled to the waveguides, and also photodiode arrays coupled as well to those waveguides, right? So these EML arrays, each one transmit at one wavelength. This AWG multiplexes all those wavelengths in one channel, and then it's coupled out to a fiber. And on the receiver side, so the different wavelengths come all together on this fiber. The AWG separates in different channels, different wavelengths, and they are detected by those photodiodes. Another crucial aspect in this project is the development of this FlexLine, this polymer-based flexible interconnects, which we use to interconnect the EML arrays with the drivers, as well as with the PD arrays with the TIA. So the polymer technology in this case allows us to scale up to this terabit per second capacities. And we are looking forward to the first results. So this project started 1 year ago, and we're looking forward to have the first results in order to show the potential of this technology. Another project, which this one is way more recent, this started this week, is called PICS. We also target for data centers terabit per second transceivers. but based on a different approach. So you can see here on the left-hand side is a multi-chip approach, so-called. So we have a controller switch ASIC that controls these different photonic integrated circuits at the edges. And here on the center, you can see what are actually these photonic integrated circuits. So basically, similarly to the previous project, we will have EML arrays and photoid arrays in order to be able to transmit at different channels, using also flex lines to interconnect the arrays of EMLs and PDs to the drivers and TIAs. And what is novel in this part is that we are not going to use wavelength division multiplexing to multiplex all the different channels. We're going to use spatial multiplexing, meaning that we are going to use multi-core fibers. On each fiber, we transmit a channel, meaning one wavelength, and the polymer is in this case used in order to come from the 3D world. So maybe they will be able to connect or to allow the connection of a multi-core fiber, and then convert or so to say route all those different cores to one plane, to one waveguide plane on which we will couple the ML and PD array. So in this case, we use the 3 photonic integration to enable this spatial division multiplexing to target these terabit per second transceivers. Another project that has been going on also since more than a year and a half, it's called Repeat. It's also targeting data centers. It also uses 3D photonic integration. So on this left-hand side, you can see here a switch module based on the combination of the PolyBoard technology on which we implement these AWGs. And we combine in this project here our technology with the silicon nitride technology from the partner Lyonics, which they have developed a silicon nitride technology called triplex. It's a very established technology, and in this case, it's this reddish area. So they implement there the different shifters and switches that I needed for the integration of this switch module. And following a similar principle, in this project, we are also targeting a vibrometer module. So basically what we do is we are able to generate an array, a 3-dimensional array at the output of the chip, which can then, so to say, shine a certain surface by means of an optical phase array. In this case, it's also implemented on the triplex technology. And by receiving the signal that we get, we can measure the vibration of a certain material that is being under fabrication. And with a similar principle, what one could use that also for LiDAR applications, for example. And this is actually a very interesting project because it shows this multi-platform approach. So the PolyBoard technology with other technologies such as the triplex technology. Also, let me mention that Mellanox is also, in this case, a part of this consortium. So moving on from data centers in the TeraWave project, another European project, also fairly new, we started in December last year. We are targeting photonic components for millimeter wave and terahertz communication. So what we aim here is to be able to generate and receive photonically wireless signals. So on the left-hand side, you can see the final goals in the project. So you can see here many different colors. Many different colors means in the end many different technologies. So we have here in the center the PolyBoard technology with a complex waveguide routing, also with some tunable lasers coupled to it. We have also phase modulators developed by the Foundry group from Moritz. We are also combining to the chip from the partner Lyonics. So this is a triplex chip. They implement optical beamforming networks there. And here on the lower side, this is a photodiode array comprising antennas. So this is actually the part that does the, so to say, the optoelectronic conversion and then shines the generated signals to space. And then the receiver counterpart is fairly simple. It's doesn't need to have the optical beamforming network, but what we use in this case are photoconductive antennas, also developed here at HHI, which detect the terahertz signal and convert it to photonic signal that then can allow us to process the information. So just to show that we can also address with our integration platform wireless communication systems. So another project on which we're working also has to do with the terahertz or the millimeter wave generation, but in this case is for metrology and spectroscopy. So this is the system that we're targeting. So it's a photonic enabled terahertz measurement system on which we have a device on the test, and we want to generate photonically a signal to couple into this millimeter wave or terahertz element, and then couple it out and measure it also with a terahertz transceiver. So the hybrid part on this in this system is this so-called photonic-based integrated signal source. So for the photonic generation, we need to generate different wavelengths that they can be photomix, and with this you can generate the millimeter wave and terahertz signal. So this PIC here will in the end comprise tunable lasers together with on-chip wavelength meters in order to be able to read out the wavelength. And this is the schematic of this photonic source that would allow generating these terahertz signals. So we have two tunable lasers. On the upper and lower sides of this PIC, we have wavelength meters comprising these free space sections to achieve etalons, thin film filters. So this shows the level of complexity that we can bring on the platform in order to be able to target this novel measurement method for terahertz and millimeter wave signals. So before I conclude, I also want to touch another application which we are currently putting a lot of effort, which is the quantum communication. So we are part of the quantum flagship project Unicorn. So very roughly, so quantum technologies have been developed during the last 10 years, and they have been demonstrated on optical benches. Now the next step is to make these technologies, as is written here, a commodity, so to say, affordable for larger volume production. So the idea is to bring those optical benches on the chip level in order to be able to miniaturize the quantum methods. And this is an example of a device that we are targeting here. So we use the different elements of the PolyBoard technology. So these U-grooves for fiber attachment, the inclusion of optical isolators, also of other materials, nonlinear materials. So these pulse poled lithium niobate, active sections, and so on. So this modular platform concept allows us to bring in a fairly easy way all these different functions on a chip level. And here is also crucial that we can also transmit shorter wavelengths. So as you can see here, we need a pump of 775 nanometers. So all that can be done on this polymer technology. And also in this project, Mellanox is a key partner. And before I conclude, I want to mention that we at HHI are part of an European one-stop shop called ACFAS 4.0. So it's an European funded project. This is a big project that allows SMEs to come in with ideas, and ACFAS finds the best, so to say, technological solution for their ideas to come up with a prototype. And if the idea happens to have a very feasible implementation either on PolyBoard or also on the indium phosphide technology, via ACFAS, the SMEs can get funding. So you can see here, ACFAS can subsidize up to 75% of these small projects for SMEs, and for larger companies up to 50%. And the idea is that a certain bureaucratic process is needed, but the idea is that within 12 weeks from the first contact, one can start this project, and in this way one can have access to our polymer technology. Not only, of course, we are always open. You can talk to us directly, and we could establish directly a project, or we could also find perhaps a potential consortium from an European project. So there are different ways to contact us. But I want to mention this specifically because this is a platform. This is a framework which allows a low barrier entry of potential interested people to our PolyBoard technology platform. And with that, I come to the end of my talk. Thank you very much for your attention. And now, shoot any questions you might have.
Yes, thank you very much. You have questions.
We couldn't hear you, Shlomo.
There are some questions on the Q&A. Can you read it?
Yes.
Okay, please.
So the first question says, please indicate the rareness of needed materials and the world market prices fluctuations. Well, I'm going to start talking first about the polymer materials that we need. So polymers or plastics have been developed during the last 40, 50 years, so they can be produced in large volumes, and the cost actually of polymer materials is fairly low. So of course the polymer materials that we use for the PolyBoard devices are engineered to have good optical properties, but they have so to say a quite established fabrication methodology, and their cost is rather low. I don't know if Moritz can answer something regarding the indium phosphide.
Yeah, so you might think that for compound semiconductors such as indium phosphide, the material costs are something to be concerned about. Namely, indium, of course, is a pretty important rare earth material because it's used in everybody's phone in the form of indium tin oxide as an electrode for displays. So if there are market price fluctuations in a material like indium, we would see this in terms of substrate prices going up. However, even there we would not see it very much, because making a clean monocrystal wafer is much more expensive than just buying the material. And then also taking into account that the substrate costs in the single-digit % range of the overall price of the finished wafers, because it's very labor-intensive and you need a very expensive clean room to process your wafers. The material prices and their fluctuations are really completely negligible for finished photonic integrated circuits. So those are not something we are concerned with.
Okay, the next one.
Shall I carry on then?
Yeah, let me just also answer on the temperature for indium phosphide. So there's basically two important flavors of indium phosphide based chips. One is semiconductor compounds that do contain aluminum, and those that don't. And our chips are solely comprised of the latter. So there's no aluminum content in our chips. And so we do not have any oxidation issues. And so temperature wise, we are pretty safe. Some people even use the chips in a non-hermetic way, so without any hermetic sealing. But for most applications, because of certain drifts of wavelength of lasers and so on, you typically operate your chips at a fixed temperature. At say 45 degrees is a pretty common operating temperature. But of course, yeah, that's not a problem for the semiconductor. So that's on the indium phosphide side. I'll let David comment on the polymer side of things.
Okay,
yeah, so regarding this hybrid, sorry, I'm going to address the same question. So how robust is the end product temperature-wise regarding the hybrid polymer-based technology? So polymers have, so to say, a high thermoptical coefficient, meaning that changes in the temperature affect the refractive index of the waveguide, and then that can influence then in the end the performance of your device. We can use that for something good, which is for tunable structures, as the tunable laser I showed. If we want to avoid that the environmental temperature influences the behavior of such PICS, including tunable lasers, as Moritz also said, we typically stabilize those devices with a tech underneath. Typical temperatures are 45 degrees or 25 degrees. Regarding to lifetime of temperature of polymer-based elements, so the polymer materials are baked during the fabrication to temperatures that are beyond 200 degrees. So this means that if you don't go beyond this 200 degrees temperature, you shouldn't destroy the polymer material. But of course, you want to always have the tech underneath so that you can control the wavelengths or the performance of these tunable structures. Yeah. That would be my part covering the temperature dependence. The last question, as I see here, is regarding free space with green lenses. What is the maximum beam diameter you expect possible? So the green lenses that we use are fiber-based green lenses. So they have a diameter of 125 micrometers. So the largest beam size is a good question. I don't know how what the maximum value is, but knowing that the cross section is 125, then the diameter would be not larger than 125 with those lenses.
Okay, Dr. Philippe and Dr. Baier, thank you very much for your very interesting lecture. I would like to continue the cooperation with you, and maybe we'll have more from your side. And I would like also to invite you to listen to our webinars. We have ongoing program, and please, you are welcome. So
thank you.
Thank you very much.
Thank you all. Have a nice day.
Bye.
Thank you very much for the opportunity.